The only thing we're going to change today is instead of looking at limits at vertical asymptotes or limits at numbers, we're going to look at limits very far away from the origin, also known as infinity. I'm talking really far away. And we're going to take about as close as we can get to a pre-calculus approach to this. Okay. So we're going to talk about limits from the left and the right. We're going to talk about a little bit of vertical asymptotes. We've done that already, but we'll work a little bit more into that just to make sure that you understand the concept of vertical asymptotes and being able to find what happens on the right-hand side or the left-hand side, whether it goes up or down, they both go up, they both go down, etc., etc. We're going to do some more stuff involving infinite limits and realizing that there, even with some infinite limits, you can still just plug and chug. We're going to talk about what happens when you get very far from the origin, and we're going to review the rules for horizontal asymptotes that you learned, hopefully you learned last year in pre-calc. Yes? Good, that'll make my life a lot easier. And then we're going to talk about what happens to the limit when the limit goes to infinity, how can you get an infinite answer? It seems like a lot, it's going to go pretty quick. Okay, so we look at this guy. I got this rational function. Why is it called a rational function? It's in a fraction, correct. It's a ratio. And it looks like that little weird V looking thing. And it seems like a silly question, but where's the horizontal asymptote? 3. Good. Technically speaking, y equals 3. What does a horizontal asymptote do? Sorry, let me review my question. What does it do?
It's like the top of the range, I guess. Like the graph can go past that.
That's not a horrible answer.
Okay.
Do you want to add anything else to it?
It will mine will keep getting closer and closer to the number.
Excellent. Okay. Just like a vertical asymptote, asymptote means it's asymptotic. Asymptotic means it gets closer and closer and closer. Let's go back to vertical asymptotes. Can a function ever cross a vertical asymptote?
No.
No, because it gives us 0 in the denominator. You knew that already. Can it cross a horizontal asymptote?
Yes.
Yes. Doesn't often, but it can. Sometimes it does this weird cross and then go back to it. But the point is, if I go very far away from this picture, what is the orange going to do as I go further and further out? If I zoom out and zoom out and zoom out, what's the orange graph going to do?
Get closer.
Gets closer and closer and closer. It might hit 3. We don't know. It's going to get really close though. Okay? So the horizontal asymptote does exactly what the vertical asymptote does, except it's horizontal. And you knew that already. If I didn't give you the picture, could you have told me where the horizontal asymptote is? How? Nathan?
Because the degree of the variables are the same, so it's going to be the coefficient of the top and the ratio of the coefficient on the x squared and then the x squared on the bottom as well.
I couldn't have said it better myself. I'm just going to click and move on. Unless anybody has a question for Nathan. No, I didn't think so. He did such a good job. So if we get some calculus, then we say the limit of the function as x approaches infinity. So now what's different today is we're getting that number that it's approaching to be infinity. So we're going way far to the left or way far to the right. Stand up, sit down. Fight, fight, fight. Very good. Does nobody know that cheer?
Where's the number?
Everywhere. It's a classic. No? Okay, anyways, let's move on. A little pre-calc review here, scenario number 1. Nathan, you want to take this? But you did such a good job with, I think it's scenario 3. Can you take a shot at it? Come on. Gesundheit. No?
I'll pass.
Okay, all right. Degree of the numerator is less than the degree of the denominator. You can all read. Then the horizontal asymptote will be the x-axis, also known as y equals x. And it's a little bit tough to see, but if the function is given up there, the degree of the numerator in this example is 2, the degree of the denominator is 3. We've talked about degrees before, yes? So we're all on the same page. You know what it did. Okay, good. I love when there's no response. Scenario 2. We don't need to talk about because they can knock it out of the park. Degree on top equals degree on the bottom. It's the ratio of the leading coefficients. And then scenario number 3, your friend and mine, Mr. Oblique Asymptote. Did you work with oblique asymptotes last year?
A little bit.
A little bit. What does one mean by a little bit? You looked at them and then you just freak out and close the book? Okay. What we're going to do, and I'm going to show you how to do this because it's really simple. We don't care what the equation of the oblique asymptote is. So for those of you that delved? What's past? It's a delve. Dove, but that's dived. Right?
I think it's delve.
Delve is different than dive. Doesn't matter. For those of you that went pretty in-depth into oblique asymptotes, you remember you probably did some long division or some synthetic division. We're not going to do that. We're concerned about one thing, and that is the slope of the line that gives you the oblique asymptote. When we deal with oblique asymptotes, the oblique asymptotes will always be linear. In other words, the degree of the numerator will be 1 more than the degree of the denominator because then when you divide it, you end up with a line. All we care about is the slope of that line. So if we use this as an example, and I'm kind of cheating because the picture's there, but if I wanted to know something about the oblique asymptote for that function, if we were going to actually find the equation of the line, I would do synthetic division, right? X cubed, or long division, 2x squared minus 1. And then you divide x cubed by 2x squared, and you go through all that business, and then you get a remainder and all that other stuff. Here's all we care about. Is that positive or negative? Positive. Is that positive or negative? Positive. So when you divide a positive by a positive, you get a positive. That's what we need to know. Can you all do that? Okay, good. Now, why do we care that it's positive? Because we know that if it's positive, it's going to be going up to the right. If it's negative, it's going to go down to the right. And we'll talk in a little bit why that's relevant, okay, when we start looking at limits. So if I look at this picture in particular, if I let x go out to infinity, in other words, I move very far to the right, what's happening to the function value? What's the y value of the function getting close to? Yes? And what's that line doing? Perfect. Going up how high? Bingo. Okay? That's what you need to be able to do. Because that slope is positive, as I go to the right, the line keeps going up. If I go out to infinity, it's going up infinity, and therefore the value is infinity. What if I go to negative infinity? Well, since I know the slope is positive and I know what that line looks like, as I go very far to the left, it continues to go very far down, and therefore we get negative infinity. Okay, that's it. I'm not going to ask you what the equation of the oblique asymptote is. We'll do virtually no or none oblique asymptote graphing problems but I will expect you to be able to determine if the slope of the oblique asymptote is positive or negative, to be able to answer those kinds of questions. Does that make sense? Hot diggity. There's some fancy terminology, which takes everything we just talked about and summarizes it into a nice little thing. The limit of the function is the same as the value of the horizontal asymptote. We saw that with the orange one in the beginning. The horizontal asymptote was at 3, therefore the limit as you approach infinity was 3. The same is true in the one, version number 2. The horizontal asymptote is at 3/2, therefore if I go very far out to infinity, the function will get closer and closer to 3/2. So this little rectangle tells you exactly what it is we've already figured out, and that is the horizontal asymptote value and the limit value are the same. Okay. Now, notice the question. Find the limit of that function as x approaches infinity 3 different ways. With your group, go. One way should be real easy. One could be a little trickier. 3 you might not even think of, so try to get all 3. One down.
Well, the expert minus x, there's another degree.
Yeah, we're finding the horizontal. We're finding
We're finding all 3 of them, so that's.
No, we're finding the same thing. I'm showing that we can find the
But the biggest the degree on top,
Yeah, I don't want
the
it.
highest degree on top is 2. This x and then x greater only one half.
What's the next one?
You just, you can only answer positive and negative. Just wipe out.
We got it.
Just shade.
You gotta know
Is that for bio? We have to do it. Like we did over. My teacher has.
Yeah, first time.
What do we used to do with
Okay, now what's the I literally said there wasn't. There wasn't.
because all the wires get tired. And also,
Use 3 different techniques. What do I plug in the job? We can get 2 over plug in 0. We can get 2 negative 2 over 7. No, actually not equal to 0 means
he means here.
expanding. That's one way of no, I mean 4x squared minus 7.
So there's a horizontal. We still have 2.
Well, the horizontal
At least exactly what that's getting.
we know the limits of it. X being equal to root 4 over something.
Yeah, I think that's
Just need Allen. Allen from what, okay?
Yeah, I don't think
Oh. I'm just going to drop that easy. Place the entire
It gave us 3 ways to solve it. Only one of those ways apply it when we agree the numerator and the denominator. So of those 3 things, of those 3 functions, only one of those uses are.
Alright, stop what you're doing. Let's talk about how to do this. Now, there are at least 3 methods, however, there are probably 4 or 5. Oh, okay, so my group has succeeded in coming up with 3 different methods. I did not help them. What did you do? Are you as cool as us? Teaching them more. No, they just lay there. Give them dead eyes. Thoughts? Dimitri, what'd you do?
We divided the leading coefficient of the numerator by the leading coefficient of the denominator.
Excellent. And got what as an answer? I don't mean to insult you, but just to make sure we're all on the same page.
3/4.
Excellent. We all agree, right? Okay, pre-calc method. I would click, but I don't remember what order I did it in, so I'm just going to leave that up there. Dimitri, did your group come up with a second method?
We did not.
So, what do you got? Also, Posey?
Grafting.
Hey! Method number 2. Hold on. Graphic. I assume you zoomed in to get that value of 3/4.
Yeah.
Bingo. Done. Excellent. Did you have a third method?
No.
Daniel? Oh wait, you had a question or did you group have another method?
I think we have another method.
Oh, do tell.
Do you plug in chug infinity?
That was our third method.
Okay.
You can't plug in infinity, but what did we plug in? We plugged in 1,000,000, and what did you get? 0.7499999925.
Okay.
Good. Now, piggybacking on that idea, what you could also do is you could go and put the function into y1 and then just scroll your brains out down the table until you get to a big honking number and see the pattern that it approaches. Okay, so quick question, do you all know what I'm talking about?
Yes.
I don't know how good your pre-calc teachers were with the calculators, but you can all do that, yes? If not, say so and I'll show you. Go ahead. Do it? Okay. Go to y1 on your calculator. Type the function into y1 on your calculator. Make sure you put the parentheses in that I included there, otherwise you'll get the wrong function. And as we do more and more work with the calculator, one of the questions you're going to have to ask yourself, is it worth the time for me to sit here and type this big rational function into my calculator? The answer, I would argue, is no, because Dimitri already told us we can find it easily by just using the leading coefficients. But we're looking for different techniques, so here's a different technique. Once you have it into y1, then go to the table. The table is above,
Above graph.
it's above graph, so second graph. And your table might be starting probably at 0, yes? Yes? Okay, scrolling will take too much time, so here's what I want you to do. Above window, it says table set. That stands for table set. Go to table set and change your starting value to something like a gabillion. Then go back to the table. You can tell the calculator, oh yeah, I'd like you to start at this number versus that number. Look at that! What did you put in? It's 156?
No.
Oh, okay. So even if you put in a million instead of a gabillion, you still see when you pull up the table, there's your value right there. It says 0.75 all the way down. Okay? Good. Any other methods? Those were our three, right? Okay. We're good? Okay, before I show you another method, I think we're up to 5. I need to talk about something. Let's suppose I have a fraction a over b. What happens when b goes to 0? What happens to the value? Now notice I didn't say when b is equal to 0. I said when b goes to 0, what happens to the value of the entire fraction? How big? What's the technical term for really big? Beautiful. A over b, whoops, I don't want that there. Well, we'll put it there. Goes to infinity. That's an important concept. Are you all good with that? Make sense? If it doesn't make sense, then think of it logically. If you make a some constant like 1, and you make b a big number like 10, you're going from 1/10, and you make it smaller down to 1 over 1, and then you make it 1 over 1/10, which would actually be 10, and the number keeps getting bigger and bigger. Okay, now, what if we take a over b, and we have b go to infinity? What happens when the denominator of a fraction gets very large? What happens to the entire fraction? Hey,
It becomes infinitely small.
also known as?
Just infinity.
It doesn't become negative, so we're not going that direction. What's infinitely small? Say 0. Good. Okay? That's going to show up a lot. And again, remember, this is calculus, so we're not talking about b becoming 0. We're talking about getting close to 0. Now, we need that with... Uh-oh. Was anybody hurt? What are you suggesting? The room is haunted? Oh, okay. Or windy. Okay. So this next method is kind of redonkulous, but it is a viable mathematical approach to a problem. So here's what I did. I took the highest degree, I know this looks like a train wreck, but wait. I took the highest degree variable, which I realized was x squared, and I divided everything by x squared. Now you're saying to yourself, self, why would you do that? Again, be patient. Okay, so the first step is dividing by the largest degree expression in the equation. I get this mess. That's legal, because really what I'm doing is I'm multiplying by 1 over x squared over 1 over x squared, which is equal to 1, which doesn't change the value of the function. Step 2, I simplify. And hopefully you can see what's going to happen here. What happens here, for instance, What happens there when x goes to infinity?
It becomes 0.
Becomes 0. Whoop. What happens when 2 over x squared when x goes to infinity? 0. And here, you're seeing a pattern. Oh, and look what we're left with. And if we agree to trust Dimitri, there's our answer. Is that a viable method? Probably not, but it is another method to get us where we need to go. Second method was the horizontal asymptote, which is what Dimitri used. And then the last one was graphing, which I forgot who came up with graphing. Posey, was that your group? There you go. Okay, you graph it and you see, oh look, it crosses the horizontal asymptote. Woo-hoo. All right, excellent. You're not always going to have a calculator though, so technique 3 is a little sketchy, if you will. All right, do that one then.
Wait, sketching, because you sketching.
Oh, I didn't even plan that. That's pretty good. I'm going to remember that for the future. Go ahead and find that limit using whatever technique you'd like. I don't care. You're driving the bus now.
That's the exact same thing that I. Oh, you're saying yes. Yeah.
Because I mean, it's not, it doesn't have a reach 5, but like it gets so close to 5, and that's what limit it.
Yeah, that's definitely fine.
Oh, yeah, I get it.
That's close to tomorrow.
Makes sense now.
Which is but tomorrow's tomorrow, but yesterday's
We really just never got It's never tomorrow. It's always
What's the answer? 5. Why? Why?
because if you plug in infinity, you just get rid of, because it's 2 over infinity, which is basically just 0, so then you're just left with 5.
Man, you're having a killer day. Let's give that one. Anybody do it differently?
So when you write it out, should you write like crossing out the 2 over x squared or something like that? To show that like that's what you did? A lot of
Make sure your notation is correct though. When you take the limit, you, as I mentioned earlier, you need to write the limit expression until the end, and at the end, then you're just giving the numerical value. So your last statement should say either equal, blah, 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 limit, yada, yada, equals 5, or just plain old 5, but you can't say the limit as x approaches infinity of 5 and leave it at that, because that's a different scenario. There is a different way to do this, and that is you could play with a little bit of algebra there. In other words, I could write the 5 as 5x squared over x squared, combine like terms, and go with that. Then I get back to a horizontal asymptote approach. I think I have that up here. Yeah. No, that's different. Split it up into 2 different parts. That's probably, I don't know. Pretend I didn't talk about that other method. I can just edit the video later. Do you feel that we answered that question sufficiently?
Yes.
Excellent. Let us move on. Oh yeah, there it is. I knew I had it in there somewhere. Get a little bit of horizontal asymptote action over there. Leading coefficient, total degree 2, 5 over 1, 5. Done. Good. Yeah. Wouldn't do that. I would do that for sure. I don't know about that. Wouldn't graph it. I don't even know what the graph looks like. Nor do I care. Okie doke. What do we do next, kids? That one. You're starting to see repetition, are you not? What's the limit? 2, done. That confirms the picture. Great, excellent. Vertical asymptotes. Quick refresher. What, skipping that? Yeah, there's, I mean, it's just the explanation where I got it from. It's a little wordy. All right, where's the vertical asymptote? Good. Be careful though. X equals -1. Where's the vertical asymptote?
1 and -1.
1 and -1. Very good. Where's the vertical Uh-oh. Your friend and mine, Mr. Trigonometry, rears his ugly head. Where is the cotangent asymptotic?
X equals sine.
Wasn't that you?
So when cotangent is it's also 1 over tangent.
Oh,
So when's the tangent?
I don't know.
First name would be
No.
Oh, it's the other
You're gonna take the cotangent of tangent.
Yeah.
We're gonna take the cotangent.
Dude, there's gotta be a
Oh, I know.
Why you might be? He's gonna get into
Yeah, but I'm saying it's using words.
Oh, yeah.
Huh?
He's white man.
No.
Don't
Don't worry, you can do it.
Yeah,
Wait, did you die? Am I talking about it? Am I just mumbling?
I still don't understand that.
Violence out of you.
Yeah, I am so bad on that. I don't
I've been talking about it.
Yes.
So whatever
All right.
is equal to 0, which would be
What's the answer?
Isn't it just 1?
0.
0 is less than x is less than pi.
I'm sorry, what was that? 0.
Is less than x is less than pi.
No. No, because they have to be, you're talking about a domain. Your domain is correct, but we want to know where the asymptotes are.
Isn't there like, I don't know how to put this into like words, but isn't there like a vertical asymptote like every, like at 0 and starting like pi, 2 pi, 3 pi, 4 pi, etc.?
I'm not laughing at you, I'm laughing at the perceived reaction I'm going to get from Abby when you explain this, because she hates this. She's made it clear Abby hates this terminology. How would you express that? Wait, hold on. Before you tell me that, how many asymptotes are there?
Infinite.
Infinite. Good. How do you express that?
That's a good question.
Well, I get paid to ask good questions. Yeah. How would I write all the infinite possible asymptotes without writing out an infinite number of pi's? Yeah, no, there's no pi repeating symbol. Go ahead, Abby, bring it home. You got this.
The value plus 2 pi k or 10, whatever.
Pi k. Because it,
Oh, yeah.
because it's a cotangent, right? Okay. So it would be pi plus pi k. Or you could do 0 plus pi k. Or you could do 2 pi plus.
How do you write that?
Hold on a second. Are you kidding me?
No, yeah.
I've never heard.
Really? Oh, my goodness. Oh, I'll need a list of pre-calc teachers' names then. Kanopki. It explains so much. Okay, we're in agreement with that, right? Oh, wait. So, and there's an infinite number of them. So, what's the period for cotangent? Pi. Right, it repeats every pi. You get, okay, good. So the way to express the infinite number is pick one of them, and technically you could pick any one, so I'm going to pick this one for no particular reason. Pi plus pi k. What does that mean? That means start at pi and add pi to it some number of times. K is an integer. Okay, so if k, for instance, was 1, you'd get 1 plus, or pi plus pi, 2 pi. If k was 2, you'd get pi plus 2 pi. If k was negative 3, you'd get pi minus 3 pi, which would give you negative 2 pi. See, senor?
So k can't be like 0.2 or something?
No.
Okay,
no,
good.
no.
Okay.
K must be
That-
integer. I'll write that down.
So like, could you write the asymptote as x?
Integer. What's that, Liam?
Hold on. Could you
Hold
write you write the asymptote then as like x equals pi plus pi k?
May.
Just write x equals pi k.
Oh, yeah. So May just had an interesting point. Can't you just write x equals pi k? Yes, if you choose to start here.
So do we have to show that we did 0 plus pi k and then it's like write again for pi k?
No.
Okay.
I'm fairly bright. I can follow that. Now, what you can't do, if we're talking tangent, you can't do that. Because 0 is not an asymptote. Pi has asymptotes at pi over 4, 3 pi, or sorry, pi over 2, 3 pi over 2, et cetera, et cetera. So it changes. If it's a sine or cosine function, this won't be pi because the period for sine and cosine is 2 pi. You never really, no, never, no? Oh, okay. I feel like I've accomplished something today. I can go home and tell my wife all about it. At least she'll be happy. Because cotangent goes from 0 to pi for that initial graph. Okay, I understand. So you're asking where I got those numbers from?
I think that cotangent is pi over 2.
No, cotangent starts at 0. If you graph one period of the cotangent, it starts at 0 and ends at pi. Tangent is the one that's split over the y-axis at pi over 2 and negative pi over 2.
Well, like, when I look at like the unit circle, would it equal like sine equals 0 like up here?
No, sine equals 0 down here. Sine relates to y. Y is equal to 0 on the x-axis.
Oh, yeah.
Okay? Yeah. What's the matter?
How did we end up
How do we do what? Oh, so the only thing that Maeve pointed out is this was my answer because I chose to start with pi. Maeve said, well, can't we just start with 0 and just do pi k because pi k is 0 plus pi k. Okay, she was showing off. Okay, it worked. Got it? Okay. Pictures. The only reason I have this is because I wanted you to be familiar with the terminology decreases without bound or increases without bound. Okay. And I don't know why the College Board wants to do this, but they do this all the time. Instead of just saying positive infinity, they say the function increases without bound. Okay, so I wanted you to be sure that you understood what that terminology was if it rolls around. Good? All right. We don't need this. You know this. Okay? But I put it up there just to say I've done it. Vertical asymptotes, what makes the denominator equal to 0? We know that 1 is a vertical asymptote. What the question is asking you, in case you didn't figure that out or understand that, it's asking you what is the limit as x approaches 1 from the negative of the function? What is the limit as x approaches 1 from the positive of the function? In other words, we've got a vertical asymptote, and I know we talked a little bit about this the other day, but it's not a bad idea to review it. We have a vertical asymptote at 1. How do you figure out if it goes both up, both down, left up, right down, and left down, right up? I think I said that right. What did we do the other day? We did do it the other day, didn't we?
Yeah.
What do you got, Posey?
You take a number that's really close to it from like the left side, so that a number gets smaller, and you plug it in, and then also
So you want to pick a number like here, whoops, or that make that appear. Okay, what number do you want to use?
0.9.
Love it. If I put 0.9 in here, do I get a positive or negative answer?
You get negative, but if you square it,
Then take a number on the other side like,
it's 1.1
love it, positive or negative?
positive.
Okay. Now, all of that work that I just did with Posey was a waste of time because it's squared. And if it's squared, it's always going to be positive. So we know that the picture looks like that. What's the answer? Say again?
Positive
And this one?
positive.
So therefore, what's this?
Limit doesn't have
Now, the follow-up to that last question in blue would be why? And your answer would be because the left-hand limit equals the right-hand limit. Infinity, infinity, infinity. Remember, if these two don't match, this has to be DNE by our definition for limits, directional limits. But since they're both infinity, we're good to go. All kinds of graphs flying all over the place. Okay, so now we're going to flip the script a little bit. There's a function. I'm not going to say anything about the function. I'm going to leave it up to you. What I would like you to do is tell me about the asymptotes and write some interesting limit questions based on that function. Where is it you would like to take the limit as x approaches? Go ahead. I'll wait.
We can do like one from writing it up, I'll write an interesting one by writing a question and then
Where is it?
Oh, wait.
It's an interesting number. That's my fault for asking. Right, I should have just gone with it.
I asked the same, so I said why not.
Okay. All right. Any others that are interesting? Hold in.
Isn't for number three? Doesn't it just approach the number
Did I
three?
answer number three for this one?
Because
Minus
2 and plus.
Remember, I don't care about the answers. I just want to see the problems. Just write me problems. Don't tell me answers. You can if you're feeling saucy, but
I wrote an answer.
Oh, I had that too.
So what are the comps?
You want some cheese to go with that wine?
Okay, I see that lysosomes can break down cells to make new ones. Necessary, and then I said like.
All right, we ready? Where's the horizontal asymptote?
3.
Excellent. Where's the vertical asymptote? -3. Very good. Okay. What limits would you want to do? What do we care about? Nathan? Come on.
Howard.
What do you got?
Oh, when x is approaching 6.397.
Does anybody want to ask him a question about that? What would you like to ask? Because I asked the same question you're about to ask. Why 6.397?
Why not?
Excellent. Good approach. I can't wait till you try that on the AP test. Other limits that you care about? Liam? Say again?
X equals 3. Negative 3.
X equals -3, correct. You could also do x equals 3 from the negative, x equals 3 from the positive, and x equals 3.
Okay, wait, also,
-3, sorry.
What about y equals 3? Is that a way to write limits? No? Okay. I thought not.
Oh, you
should have.
Because remember, a limit is always, as you approach this x value, the value of the limit is the y value that it spits out.
Okay.
Okay. What are the only other two we care about?
Infinity and
Infinity and negative infinity. Very good. Okay. We know this already. Okay, so I'm just going to go through this quickly.
So at x.
When we talk about the fact that you decrease without bound or increase without bound, it is possible as you go very far away from the origin, to the right or to the left, that the function can continue to get bigger and bigger. It's not always going to approach a number per se. You could get infinity and negative infinity as answers. We talked about this already when we talked about the oblique asymptote, but you also see in this picture for x cubed, what happens is I go very far to the right, the function continues to go up and up and up. And as it continues to go up and up and up, when it approaches infinity to the right, the function itself approaches infinity. As I approach infinity to the left, also known as negative infinity, the function keeps going down. Okay. So, a limit as x approaches infinity will not always be a numerical value, it can also be infinity and negative infinity. Does that seem pretty straightforward? Okay, good. Keeps going up, keeps going up. We're all good. Okay. Questions? Lovely. Let me stop this.
Yeah.